In this video, we're going to cover section 1.4 on differentiation using limits of difference quotients. This is the first section where we define the first main concept of calculus known as the derivative. So the objective is to be able to find derivatives and values of derivatives using a definition, and then we'll also interpret that by finding equations of tangent lines. All right, so our definition, slope of a tangent line. So a tangent line, first of all, before we talk about this definition, is a line that touches the curve at exactly 1 point versus the secant line we talked about in the last section touches a curve at 2 points. All right, so in this picture here, at the point P, this pink line that we see here would represent what we call the tangent line. It's the line that is tangent to the curve that just touches it just at that point P only. And it's found by, if I were to think of my secant line as going from P through Q1, and then, so starting out here with my second point of my difference quotient being this value, and then sliding it closer and closer and closer to P, and looking at the value of the slope of the line through P in Q1, and the slope of the line through P in Q2, then through P in Q3, and through P in Q4, and look at the limit of what happens as this point slides closer along the curve and gets closer to P. That's what's happening as I move from Q1 to Q2 to Q3 and to Q4. So what's happening when I do that is that the value of H, which is the distance between the X values here, is shrinking. It's getting smaller. So we're going to define our slope of this tangent line right here to be the limit as H approaches 0 of our difference quotient. This was the slope of our secant lines between any of those points, Q1, Q2, Q3, and Q4, and P. But if I shrink the distance away from that point, any one of those particular points in P, meaning taking the limit as H approaches 0, we end up getting closer to the value of the slope of this pink line. This is also called instantaneous rate of change. Average rate of change is just the average slope between two values. Instantaneous rate of change is the slope at one value. Okay, that's the difference. So for a function, f of x, its derivative, so that term derivative, defined by the notation f prime, is defined by the instantaneous rate of change, or the slope of the tangent line to the curve at that point. So f prime of x, meaning that we're finding the derivative of the function f, we take the limit as h approaches 0, f of x plus h minus f of x over h. So it is the slope of the tangent line at a point. 1 point on the graph is defined to be the meaning of the derivative. Okay, and that is provided our limit exists. And then if f prime, or the derivative of f, exists, then we say that our function is differentiable. All right, so our first example, we're going to use the function x squared, find f prime of x. Then after we find the function that represents our derivative, we're going to evaluate it for -3 and 4. So f prime of x equals limit as h approaches 0, f of x plus h minus f of x over h. So if our function is x squared, f of x plus h is x plus h squared, minus f of x, which is x squared, divided by h. FOIL, so we're going to clean this up. FOILing this out, x squared plus 2xh plus h squared, followed by the minus x squared up here, allows the x squares to cancel, leaving you with just these terms. From these terms, you can factor an h out, leaving 2x plus h. Once the h is factored out, it can cancel with the h on the bottom. So we have the limit as h approaches 0 of 2x plus h left over. Just calculating the difference quotient for the function x squared and taking the limit as h approaches 0 to get f prime. So this is our limit laws, right? This is a polynomial using x's and h's. If h is getting close to 0, I can substitute a 0 for h and just get 2x. So f prime of x is 2x. So that's a formula that represents the derivative, or the slope of the tangent line, to the curve x squared for any value of x. So f prime of x equals 2x. They want us to find f prime of negative 3. So just plug negative 3 into that function. So 2 times negative 3 would be negative 6. And then they wanted you to find f prime of 4. So 2 times 4 would be 8. So negative 6 would be the slope of the tangent line to my function x squared if the x value were negative 3. And 8 would be the slope of the tangent line to the function x squared if the x value were 4. So next we're going to do the same thing, only for the function x cubed. Find f prime using our difference quotient and our limit definition for derivative, and then find f prime of negative 1 and f prime of 1.5. So f prime of x, again, is the limit as h approaches 0, f of x plus h minus f of x over h. So we plug x plus h into our function. So x plus h cubed minus the function f of x, which is x cubed, divided by h. Same as before, we have to FOIL this out. So you have to write out x plus h times x plus h times x plus h, do all the FOILing, combining like terms, and you will get x cubed plus 3x squared h plus 3xh squared plus h cubed. Then the minus x cubed sits behind all of that on the top. Once that's been expanded out, the x cubes can cancel. Once those cancel, the leftover terms you can factor an h out of, leaving 3x squared plus 3xh plus h squared. Then that h that gets canceled can cancel with the h on the bottom, leaving 3x squared plus 3xh plus h squared. We still have our limit notation sitting in the front. So if h is approaching 0, all the h's get replaced with 0. So this h becomes 0, meaning that term goes away, and this h becomes 0, meaning that term goes away, leaving just 3x squared as our answer. So if our f prime of x equals 3x squared, f prime of negative 1, we plug a negative 1 into that and get 3. And f prime of 1.5, this should say of 1.5, we're plugging in a 1.5 into here, squaring the 1.5, multiplying by 3, 6.75. So this means that the slope of the tangent line to the function x cubed when x is negative 1 is 3. And the slope of the tangent line to the function x cubed when x is 1.5 is 6.75. All right, so use the results of examples 1 and 2 to find the derivative of the function x cubed plus x squared, then calculate f prime of negative 2 and f prime of 4, and interpret the results. All right, so in example 1, we did the derivative of x squared, and we got 2x. And in example 2, we did the derivative of x cubed, and we got 3x squared. So that limit property, back from the previous section, section 1.1, the f prime of x, this is f of x, f prime would be the derivative of this function plus the derivative of this function, so the 3x squared plus the 2x. We'll get into in the next section, I think, learning shortcuts of finding those derivatives without having to go through the whole long definition. All right, now you're going to plug negative 2 into your derivative formula to get f prime of negative 2. Evaluate that, you would get 8. Next, plug 4 into your derivative formula. So f prime of 4, 3 times 4 squared plus 2 times 4. 48 plus 8 is 56. And then these results mean that when x is negative 2, right here, the slope of the tangent line is 8, that was the answer. When the x value was 4, right here, the slope of the tangent line to my curve was 56. So if you had graphed the function f of x, which was x cubed plus x squared, and found x value negative 2 and drew a tangent line, that line's slope is 8. And if you found 4 on that graph and drew a tangent line, that slope is 56. All right, third example. When f of x equals 3 over x, find f prime. Then find f prime of 2. And then we're going to find an equation of a tangent line, not just the slope of the tangent line. This will be the slope of the tangent line. Then we're going to find the equation of the tangent line at that spot. All right, so f prime of x is the limit as h approaches 0, f of x plus h minus f of x over h. So our function was 3 over x. So 3 over x plus h minus 3 over x, all divided by h. This is a rational function. I think it was the same one we did in the previous section, but you're going to get a common denominator. So that would be x plus h times x. So rewrite both fractions with the common denominator. Gets me this. Distributing the negative sign through the parentheses gets me to here. Then my 3x's cancel out. Once the 3x's cancel out, oops, sorry, hold on. Back to here. Once the 3x's cancel out right here, you get negative 3h on top over x times x plus h on the bottom, still with the h underneath it all from here. So this h from the top here cancels the h on the bottom, negative 3 over x times x plus h. Then take your limit. Once you get all cleaned up, let h be 0. So if this h is 0 and it cancels, you still got your negative 3 on top, but if the h is 0, you got x times x. That's x squared. So you get negative 3 over x squared. So if f prime is negative 3 over x squared, f prime of 2, negative 3 over 2 squared, so negative 3/4. That's the slope of the tangent line for the x value of 2. All right, part C wanted an equation of a tangent line. So when x is 2, we just found our slope to be negative 3/4. So the other thing you need if you're writing the equation of a tangent line is you need an ordered pair. You have your slope figured out from your derivative already. Now you're going to find the y-coordinate of your point. So to get the y-coordinate of the ordered pair, right, you're given the x value of 2, you're going to find f of 2. So plugging 2 into the function, 3 over x would be 3 over 2. So our equation for a line, slope-intercept, y equals mx plus b. So we're going to plug in, this was the y value of our point, 3/2. Our x value is 2. We're just plugging those in, y and x. And then our m value was our derivative value, negative 3/4. We're going to solve this for b. So negative 3/4 times 2 is negative 3/2. Adding 3/2 to both sides, 3/2 plus 3/2 is 3. So b is 3. So the equation of your tangent line is y equals your m, negative 3/4 times x plus your b. So we did writing equations of lines back in chapter R. This is an application of that. And calculating slopes. All right, here we're going to repeat example 3a. In other words, finding the derivative of this function. Instead of using the function 3 over x, we're going to use negative 2 over x. And then since it's similar, they're asking what are the similarities in the method. All right, so our formula for f prime is the same. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. So this time our function is negative 2 over x. So negative 2 over x plus h minus negative 2 over x. That's the function f, subtracting it, dividing it by h. Get a common denominator, which is again, x plus h times x. Compensate for so this denominator would need to get multiplied by x, so does the top. This denominator needs multiplied by x plus h, which means so does the top. So these two negatives became a plus sign here, but otherwise we get negative 2x plus 2 times the x plus h over the common denominator. That's just cleaning up the numerator. Distribute the 2 through the parentheses, so you get negative 2x plus 2h. Nothing else changes. Notice the 2x's cancel. So you're left with 2h over the x times x plus h with the h on the bottom. Again, the h's cancel. And you're left then with 2 over x times x plus h. Once you get all that cleaned up to here, now you can let h become 0. You cannot let h become 0 and plug that in until this bottom h here gets canceled out, which doesn't happen until the very last step. But after that is done, now you can replace h with 0. So if this h gets replaced with 0, x times x is x squared. So we get 2 over x squared is our answer. So both methods had the same basic principle. We started with the same formula. Break it down until you don't have an h anywhere in the equation. So you simplify it all the way down first, then you plug in any values for h and being 0, and then clean it up. All right, the next part of this section is learning how to decide if a function is differentiable from a graph. Okay, so does the derivative exist? And you can look at characteristics of a graph to decide that. So a function f of x is not differentiable at a point A if, first of all, there is a corner. So any of these cases where there's a sharp corner, right, or abrupt turns here where there's kind of sharp edges or corners. So any of those places would indicate that the function does not have a derivative at those values of A. It also will not have a derivative at a point if there is a vertical tangent line. So if you're drawing in a tangent line that follows along your curve and it's running vertical up and down, right? So if I'm following along my curve here, my tangent line that hits the point 1, that hits my graph one time right here runs vertical. Remember, the slope of a vertical line is undefined, and the slope represents the derivative. So if the slope of that line is undefined, that means the derivative is undefined and it does not exist. So it's not differentiable in that situation. So a function f of x is not differentiable at a point also when it's not continuous at the point. All right, so here's an example. G of x is not continuous at -2, right? Because the limit doesn't exist, because the left-hand limit and the right-hand limit are different. So it can't be differentiable at -2. So the three possible places to identify non-differentiability on a graph is a corner, a vertical tangent line, and a discontinuity. All right, so where is this function f of x equals the absolute value of x minus 6 not differentiable? So let's think back to what we know about what this graph looks like. Absolute value graphs are a shape of a V, and this is x minus 6 on the inside. That would cause the V shape to move to the right 6 places. So your corner of the V occurs at, if it moves to the right 6 from the origin, it occurs at x equals 6. So if you imagine the graph of this function, it has a corner at the x value of 6, so it shouldn't be differentiable when x is 6. All right, so they just say that here. This function is not differentiable at 6. This is the vertex of your function, right, or that corner point of the V, and that's a condition for it being non-differentiable. Now, if you don't remember what let's go back here before we move on to summary. If you don't just know off the top of your head what the graph looks like, since all the criteria for identifying non-differentiability is looking at a graph, you can graph it on your calculator, right, or make a table of values, but you have to know what the graph looks like to identify that. All right, so our summary. A tangent line is a line that touches a smooth curve at a single point. Okay, it references pages in your textbook for more examples. The derivative of a function is defined to be f prime of x equals, it's the limit as x, should say h approaches 0, f of x plus h minus f of x over h, the limit as h approaches 0 of your difference quotient. The slope of the tangent line at A is the value of the derivative at A. So if you find the derivative and plug in a point, that's the slope of the tangent line at that x value. Slopes of tangent lines are interpreted as instantaneous rates of change. They're the slope at one point, not an average value of the slope between 2 points. The equation of the tangent line is found by simplifying. They've shown this is the point slope formula. We did it in the example, using slope-intercept, so either way, but point slope is y minus the y value of your point is f of a equals your slope at the point, that's the derivative evaluated at your point, that's your slope, times x minus the value of x. If a function is differentiable at a point, then it's continuous. So if it's differentiable, you automatically have continuity. However, the reverse is not true. Continuity at a point does not imply differentiability. So an example of that is your absolute value function, kind of like the last example we talked about. So if I just had absolute value of x, or any graph where we have a corner, that function is continuous. You could draw that v without lifting up your pencil, right? But it's not differentiable at that corner, right? Because a corner is a point, right, where the derivative would not exist. So just because it's continuous does not necessarily mean it's differentiable, right? It's not differentiable if there's a discontinuity, if there's a corner, or if there is a vertical tangent line. Right, and that is the end of section 1.4.